All right, it's 2 o'clock, so let's go ahead and begin. If you are here, please type the word "here" into the chat on Zoom. Today, we are going to be talking about the superposition principle, and I'm going to supplement this with a discussion of linearity. The superposition principle states that in any linear network, the voltage across or current through any element or source may be calculated by adding algebraically the individual voltages or currents caused by the separate independent sources acting alone with all other independent voltage sources being replaced by short circuits independent current sources being replaced by open circuits. So there's a lot of words here, but effectively what the superposition principle boils down to is if we have a linear network containing multiple independent sources, does not matter whether they are voltage sources, current sources, or any combination thereof, we can analyze that circuit with only one independent source on at a time, add up all of our results, and we should get the exact same result as if we had analyzed the circuit with all of the sources on at the same time. So I'd like to demonstrate that to you. Okay. So let's say that we have the following circuit. Where we have a 6-volt source 6 ohm resistor, a 10 ohm resistor, a 9 ohm resistor, and a 2 amp source. Our quantity of interest will be the current flowing through the 10 ohm resistor with a direction down, which I have labeled IX. Okay. So what we are going to do is we're going to analyze this circuit with both sources on using all of the circuit analysis techniques that we've learned to this point. And then we're going to reanalyze this circuit with only the voltage source on, and then again with only the current source on, and combine those results and see if they match the result when we had everything on. Okay. So in order for us to determine the value of this current IX, what I'm going to do is I'm going to label some other quantities that may be of use to us. So for instance, I'm going to call this current flowing through the 6 ohm resistor in this particular direction I6. I'm going to call the voltage drop across the 6 ohm resistor V6, having this particular polarity. I'm going to call the voltage drop across the 10 ohm resistor V10, and the current is already defined to be IX. I'm going to call the voltage drop across the 9 ohm resistor V9, and we can easily observe that the current flowing through the 9 ohm resistor is just the 2 amps provided by the source on the right. So what I'm going to do now is I'm going to apply Kirchhoff's current law at that top middle node. And I'm going to say that all of the currents that are leaving are positive, and all of the currents that are entering the node are negative. So I'm going to have negative I6 plus IX minus 2 amps is equal to 0. And I'm going to write a Kirchhoff's voltage law loop, AVL, around the left-hand loop, which will look like negative 6 volts plus V6 plus V10 is equal to 0. And I now have 2 equations and 4 unknowns, but I can use Ohm's law to relate the quantities V6 and I6 and V10 and IX, right? So using Ohm's law, I can say that V6 is simply 6 ohms times I6. And I can say that V10 is equal to 10 ohms times IX. And what I'm going to do now is make some substitutions here and rearrange my equations slightly. So for instance, for this first KCL equation, I'm just going to move the constant term to the right-hand side of the equal sign, giving me negative I6 plus IX is equal to positive 2 amps. And I'm going to substitute in my Ohm's law relationships into my KVL equation and also move the constant term to the right-hand side of the equal sign. So this should give me V6, which is 6 ohms times I6 plus V10, which is 10 ohms times IX is equal to 6 volts. And I now have a system containing 2 equations and 2 unknowns. We are very regularly going to have to solve systems of equations in this class. So I would like for you all to use the next few minutes to familiarize yourself with your system solvers on your calculator. And I would like for you to verify whether or not you get the same results that I do. So I got I6 to be negative 7/8 of an amp, and I got IX to be positive 9/8 of an amp. I'm going to put a box around IX because that was the quantity. Now, the analysis that I did here wasn't particularly difficult, or at least I didn't feel so. But it was rather tedious because we had to develop multiple relationships and literally use practically every circuit analysis technique that we've learned up to this point in order to analyze the circuit. Okay. What I would like for us to do now is to use the superposition technique to see if that makes our analysis any easier. So what we're going to do now is analyze the circuit with our voltage source on and our current source off. So this new circuit will look like this, where we have our 6-volt source, our 6 ohm resistor, our 10 ohm resistor, our 9 ohm resistor, and the superposition principle tells us that we turn off an independent current source by replacing it with an open circuit. So the reason why we do this is because we want our off current source to supply 0 amps of current, and we know that no current or 0 amps of current can flow through an open circuit. I'm going to label my current of interest IX, but I'm going to designate it with a prime here. This prime simply means that this is the first iteration of superposition that I'm doing. When we do our analysis with our voltage source off and our current source on, I'm going to call that current IX double prime. If there were 3 sources, I would have an IX triple prime. If there were 10 sources, I would have an IX to that X power. Okay. All right, so how might we go about determining this current IX prime when our current source is off? Anybody have any thoughts? So I would argue that we can just use Ohm's law, where we can see that IX prime will be 6 volts divided by the 6 ohm resistor in series with the 10 ohm resistor, which is going to look like 6 over 16 or 3/8 of an amp. The analysis that we had to do to solve for IX prime was fairly straightforward, I believe. Now let's look at what happens with DS off, our voltage source off, and our current source on. Okay. So according to the superposition principle, we turn off a voltage source by replacing it with a short circuit, because we want to force a 0 volt drop across where the voltage source was, which is the same as having a off voltage source. So our voltage source is replaced by a short circuit. Here we have our 6 ohm resistor. Here we have our 10 ohm resistor. Here is our 9 ohm resistor. Here is our 2 amp source. And oops. As I mentioned a few moments ago, I'm going to label this current IX double prime. And I can solve for the current IX double prime using current division, which we discussed in yesterday's class. So using current division, I'm going to have 2 amps because that's the amount of current that's flowing through the 9 ohm resistor and then sees the parallel resistive network. And since I want the current through the 10 ohm resistor, I'm going to have 1 over 10 ohms. And then in my denominator, I'm going to have the sum of the reciprocals of the resistors that are in parallel. So that's going to be 1 over 6 ohms plus 1 over 10 ohms. And I'm going to throw this into my calculator real quick. And I get 3/4 of an amp, which is the same as 6/8 of an amp. What I'm going to do now, I'm going to do this in blue, is I'm simply going to combine these results. So IX should be equal to IX prime plus IX double prime, or 3/8 plus 6/8, which is 9/8 of an amp. This exactly matches the result we got with both of our sources on at the same time. But I would argue that the analysis that we had to do was easier when we use the superposition principle for this particular circuit. All right, so I would like to expand on the superposition principle by talking about the concept of linearity. Linearity can be a difficult concept to understand because it's rooted in signal and system theory more so than circuit theory. So you'll have to indulge me for a few minutes and then I'll bring things back around to how it applies to circuits, okay? So let's say that we have a black box system. That is representative of a linear circuit, okay? On the left-hand side, we will represent our input signals. So these would be representative of our independent sources. I'm going to call my first input signal X1. And I'm going to call my second input signal X2 of t. I'm going to observe that my system has two different outputs. Y1 of t and Y2 of t. My system acts on, let me line these up, that's going to bother me. My system acts on the input signals to generate the output signals. And the way that that is described is with a transfer function, h of x. So if my system is linear, then my system response must satisfy the following equation. H, my transfer function, acting on alpha x1 of t plus beta x2 of t will yield an output of alpha y1 of t plus beta y2 of t. Or another way that we can think about it is my system is acting on an input signal x of t, which is simply decomposed into alpha, some scaling factor, times x1 of t, plus beta, a different scaling factor, times x2 of t, and generates a result y of t, which is simply the combination of alpha y1 of t plus beta y2 of t. This mathematical statement here, which I fully understand that the overwhelming majority of you don't follow, is really just two distinct independent properties that must be satisfied simultaneously to prove whether or not a system is linear. And these two properties are additivity and homogeneity. Or scaling. So we're going to look at the additivity property first. Additivity property states that if several independent inputs are used to excite the system, the total response, which is just a fancy word for output, due to all of these excitations determined by considering each input separately while assuming all other inputs to be zero. This statement is literally the exact same thing as the superposition principle that we talked about earlier. We can analyze a circuit by considering each independent source on by itself and then combining the results. That is all the additivity property states, and we have effectively already covered that portion. Now let's talk about the homogeneity property. The homogeneity property states if an independent input is used to excite a system, scaling that input by an arbitrary factor of alpha where in this case, alpha is literally just any non-time varying quantity. So that means it could be a number, like it doesn't matter whether it's an integer or a non-integer, if it's rational or irrational, if it's real or imaginary or complex, all of those things are okay as long as it doesn't change. So see, scaling that input by an arbitrary factor of alpha causes the output to be scaled by the same amount. So let's put this into circuit terms, okay? If we analyzed the circuit that we had earlier, where we had a 6-volt source, a 6-ohm resistor, 10 ohm resistor through which a current IX flows. A 9 ohm resistor and our 2 amp source, right? We observed in 2 different ways at this point that our current IX came out to be 9/8 of an amp. What the homogeneity property states is that if I scale my inputs by an arbitrary factor, let's say 2, my output should scale by the same amount. Meaning that if I replaced my 6-volt source with a 12-volt source, and I replaced my 2 amp source with a 4 amp source, I should find that IX will be twice as large, or 9/4 of an amp in this case. So if I scale my inputs by a factor, the output has to scale by the same factor. So let's see whether or not that works out for this particular circuit. So I'm going to call this voltage V6, this current I6, this voltage V10, because these are the only quantities that I used the last time I solved this circuit. I'm just going to use these again. Applying KCL, I should see that I have negative, excuse me, this will write negative I6 plus IX is equal to 4 amps. And I should have 6 ohms times IX, excuse me, times I6 plus 10 ohms times IX is equal to 12 volts. And when I solve this system simultaneously, I'm going to do that real quick in my calculator simply by changing the constant terms in my previously stored solve here. So that's 4, that's 12. And I get negative 7/4 of an amp for I6, which is exactly twice as large as it was previously. And I get 9/4 of an amp for IX, which is exactly what was predicted if the scaling property or homogeneity property were to hold true for this particular circuit. So we have observed that this particular circuit obeys the additivity property or the superposition principle, and it obeys the homogeneity property or the scaling property. But we have verified that independently. And so what I mean by that is we need to see whether or not it's true when both are applied simultaneously. So what I'm going to do, I'm going to go to the next page here, and I'm going to summarize the results that we've gotten thus far. So our input signals I'm going to put on the left, and our output I'm going to place on the right. So the first time we analyzed the circuit, we did it with a 6-volt source and a 2 amp current source on at the same time. And we observed that IX, our output, was 9/8 of an amp. Then we analyzed the circuit with the 6-volt source on by itself and saw that the result was 3/8 of an amp. We analyzed the circuit with a 2-amp source on by itself and observed that our result was 6 of an amp. And then we analyzed the circuit with a scaling factor of 2 being applied so that we had twice the 6-volt source on and twice the 2-amp source on, and we got 9/4 of an amp. So what I want us to do now is to use these properties to make some predictions regarding the behavior of our circuit. And then we're going to do some analysis and find out whether or not our prediction is correct. So what would happen to our output current IX if we scaled our voltage source by a factor of -3? So if we had our 6-volt input and we scaled this by a factor of -3, what should we expect the output to be in that particular case? Anybody have any thoughts? So we just need to look at this bit in our table, okay? So when we had a 6-volt source on by itself, we observed that our current at the output was 3/8 of an amp. If we scale our input by a factor of -3, we should scale our output by that same factor of -3. So I predict that we would see -9/8 of an amp at the output. Does that make sense?
Yes.
All right. So now what if I scaled my 2-amp current source by a factor of +5? Well, looking at our table, I would simply scale that 6/8 of an amp output by a factor of +5 as well. 6/8 times 5 is 30/8. And now, here's the interesting bit. Let's apply this together, okay? So if we scale our voltage source by a factor of -3, and we scale our current source by a factor of +5, we should expect to get an output that is the sum of our previous two results, which to me looks like 21/8 amps, if I did my math here correctly. So let's analyze exactly this circuit, okay? So if I scale my voltage source by a factor of -3, so I have a 6-volt source multiplied by 3 is going to be 18 volts. The negative sign means I need to change the polarity of my voltage source. So I'm going to have negative on top, positive on bottom, 18 volts. Here's my 6-ohm resistor. Here's my 10-ohm resistor that I'm trying to find IX through. Here's my 9-ohm resistor. Here is my current source. Since I'm scaling my 2 amps by a factor of 5, this is going to look like a 10-amp current source. And as before, I'm going to call this voltage V6, this voltage V10, and this current I6. When I apply KCL at this top middle node, I'm going to have I6 flowing in, IX flowing out, and minus 10 amps flowing in is equal to 0. Rearranging slightly, this looks like negative I6, excuse me, plus IX is equal to positive 10 amps. Writing a Kirchhoff's voltage law equation around the left-hand loop, I'm going to have positive 18 volts plus V6 plus V10 is equal to 0. Using the Ohm's law relationships that we developed earlier, this looks like 6 ohms times I6 plus 10 ohms times IX is equal to negative 18 volts. And here's my equation 1, here's my equation 2. If I solve these simultaneously, I find that I6 will have a value and IX will have a value. I'm just going to throw this in my calculator real quick. So I get I6 to be negative 59 over 8 amps and IX to be positive 21 over 8 amps. Exactly what we had predicted based on the results of our previous circuit analysis. Okay. So this is why I believe that only teaching the superposition principle is really only giving you guys half of the power that linearity can provide. Effectively, with the scaling property or with the homogeneity property, we can work a circuit with any voltage source value or any current source value that we feel like and determine what would happen if we scaled that up to whatever that we were asked for. We are going to use this principle at several points throughout the rest of this class. So I just wanted to introduce it to you formally, then hand waving it when we use it later on. Okay. So that's all that I had prepared regarding the lecture. I want to talk to you very briefly about your in-class assignment homework set, your in-class assignment for this material, as well as the homework problems that are associated with it for web work. So bear with me just a moment. So let's look at the in-class assignment first. So let's see. Number 5, I believe. All right. So if I'm not mistaken, there's only the one problem, but it's broken up into 4 parts. Part A asks you to determine the contribution of the 1 amp current source to the voltage Vx. What I mean by that statement is leave the 1 amp source on, turn the 5 volt source off, and tell me what Vx prime is. For part B, I ask you to determine the contribution of the 5 volt voltage source to the voltage Vx, meaning you leave the 5 volt source on and turn the 1 amp source off. This is exactly how I am going to phrase the questions on your exam that require you to use superposition. Okay. For part C, you simply need to add the results of parts A and B together. So apply the additivity property. And then for part D, I say if the voltage source were replaced with a 3 volt source, so that's really scaling the voltage source by a factor of 0.6. Actually, positive polarity on bottom means we're scaling the voltage source by a factor of negative 0.6. And then it follows, the current source were replaced with a 2.5 amp source direction up. That means we're scaling the current source by a factor of 2.5. Use the properties of linearity to determine the value of Vx under these conditions. All you have to do is take the results from part A and part B, Scale the result from part A by a factor of 2.5, scale the result from part B by a factor of negative 0.6, add the results together, and you should be good to go. I only expect you to use actual circuit analysis for parts A and B. Everything else you can do just with manipulation of algebra and understanding the two different properties that give us linearity. You don't need to actually analyze the circuit at all for part C or D. All right, now I'm going to pull up the web work. Looking at set number 5, let's look at problem 1. All right, so problem 1 doesn't have anything to do with superposition or linearity. You're asked to use source and resistance combinations in order to determine things. So this problem is really just review of things. Then we have problem 2. This particular problem can be greatly simplified by applying the concept of homogeneity or scaling, meaning that if you solve part A, you immediately know how to do or the answer to part B with no circuit analysis whatsoever, or vice versa. If you're able to solve B, then you can use the scaling factor to determine A, and then C is simply the ratio of your results, okay? So this is a great problem to practice the application of the scaling property. Only do analysis for A or B, and then use the scaling property to get the other result. For problem number 3, first off, let me say that I think it's unfortunate that they give you 3 different circuits to analyze for one problem. So sorry, whoever wrote this was mean. Part A of the circuit is an actual good circuit to use to practice superposition. Parts B and C, you're going to wind up, even using superposition, developing a system of equations that you will have to solve to determine the quantity I, Y, and Vx respectively. What we're going to be learning about for our next 2 class meetings will be nodal analysis and mesh analysis, which are very formulaic means for writing systems of equations to solve circuits. So I would argue that you should wait to work part B and C of this particular problem until we learn nodal analysis and or mesh analysis. It will actually be much easier than trying to force superposition to work for these particular circuits, okay? So B and C, again, I cannot emphasize this enough, they're not particularly good circuits for illustrating the usefulness of superposition. Finally, let's look at problem number 4. Problem number 4 is actually a good circuit that will allow you to use the superposition principle. It will actually also reinforce, when you're using superposition, voltage division and current division relationships. So I think this is a very strong candidate to actually use the superposition principle. All right, those are the 4 problems from your homework set. I hope that I have identified any particular pitfalls and things like that that you may face on those problems. We've also discussed my expectations for the in-class assignment. If anybody has any questions, I will hang out here on Zoom. If not, I hope you have a great rest of your afternoon, and I will see you on Thursday.